All right, my friends. I went kind of long with the last lecture, so we're going to make this one a shorter lecture, and then you guys can spend whatever time you haven't spent watching me talk, working on your homework or your lab or your poster. There's plenty of stuff to do. Okay, so we're going to talk about magmatic diversification, and then we're going to pick up all the rest of the stuff that I'll move some stuff around, and we'll start talking about basalts pretty quick here. And as we talk about basalts, we're going to talk about volcanic eruptions of basalts. We're going to talk about what a basalt will look like. We're going to talk about the chemistry of the basalts and stuff like that. But there's just one more bit of information that we have to feel comfortable with, and that is how do we diversify magma even more? So we've talked about where we get the magma. We've talked about the ways that we can get the magma, but how does it become different? If we are melting the mantle, how do we get a rhyolite? So let's jump into this and make sure that I'm actually recording, and I am, just to make sure, because it'd be really dumb to talk to myself this whole time. All right, so let's talk about magmatic differentiation. So we've looked at this picture before, and we've seen that there is all this variation in magma. So what causes the diversity of magma, not just in the whole world, but also from volcanoes? From one volcano can have a huge amount of diversification. So let's talk about what causes that. There are a number of different ways to diversify magma. Okay, so you've got magma, and there's a number of different things you can do to it to get different chemistries out of it. The most important ones are partial melting and fractional crystallization. Assimilation, magma mixing are minor importance. And then liquid immiscibility, we'll talk about. It's not a super important part of it, but it does exist in a few weird places, so we need to talk about it. All right, so we'll start and talk about, what is partial melting? Partial melting is when you have a rock and you melt it, but you don't melt it all. We've been talking about this for a long time. That has its name. It's called partial melting, all right? Some, but not all of the rock's minerals melt to create the magma. Fractional crystallization means that you're actually going the other direction. Okay, we're crystallizing. We actually have a melt, we're starting to crystallize it, and then all of a sudden we've crystallized it, but the solid gets separated from the liquid. And the liquid is taken off somewhere else, and the solid is left alone. So that's another way you can diversify. Assimilation is something that doesn't happen very frequently, but it's when magma melts the surrounding rock and then kind of assimilates it. Okay. That's why it's called assimilation. So it kind of like eats it up and causes the stuff around it to become part of itself. That sounded a lot more brutal than I was thinking. And then we have magma mixing, and that's literally you have one magma and you have another magma and you mix them together. Voila. And then liquid immiscibility is basically when the magma cools, parts of it do not want to mix well with others, and so it separates, like oil and water. So let's talk about partial melting to begin with. And we have talked about this already, so let's just make sure we're all on the same page. You'll remember that some minerals will congruently melt, which means when they're melting, if you have a mineral of a certain composition, your melt is going to be the exact same composition no matter how much or how little of the crystal itself melted. So that is like quartz. Incongruent melting, excuse me, is when the composition of the melt is different from the original solid. And so as you are melting, your liquid is a different chemical composition than your solid. So melts and crystals of different compositions coexist. And this is far more common with our major rock forming minerals. And then we talked about plagioclase and how plagioclase was an example of this. Plagioclase, the first thing that melts is always going to be sodium rich. Okay, and that's going to leave the crystal to be anorthitic rich. And of course, the opposite is true. The very first thing that crystallizes is going to be calcium rich. It'll be anorthitic, okay? And this has implications for magma composition because if you can separate those, then you are going to start seeing some very different chemistries. So partial melting of minerals produces melts that are not the same composition as the parent material. Now, there's two different ways you can partially melt something, okay? The first way is called equilibrium partial melting, all right? Equilibrium partial melting, you're taking something that's a solid, you're starting to melt it, but it's a closed system. All right. So imagine a container, the liquid cannot get anywhere. The solid cannot go anywhere. They always are in contact with each other. So in a closed system or equilibrium melting, your melt and your solid are going to remain in contact. And they're going to be able to communicate with each other. Communicate meaning they're going to stay they're going to be able to move atoms around. So basically, what's happening in a closed system, as you get more and more melt, um, that melt is going to evolve to be closer and closer to the original parent rock. But imagine this in your mind. If you had a rock, you started to melt it, and then you got quite a little bit of melt, and that melt is a different composition than the original rock, and then you froze it again. Well, that's all one rock, but now you're going to have different parts of it that are going to have very different compositions. So even though the bulk composition is the same, you're going to start seeing some weird things, okay? Your minerals that are present, they're going to start altering. Your solid solutions are going to start shifting composition. But as long as you melt the whole thing is going to have the same composition as your original rock was. Unsurprisingly, this is not common. We do not see a ton of equilibrium melting. It can happen. It happens in small amounts and stuff like small batches, but way more common is disequilibrium partial melting. And this is when you have an open system. Now, there's not a lot of jars that are holding pieces of rock so that they can't separate the liquid from the solid. And remember that the liquid is going to be less dense than the solid, so it's going to want to move more freely. So open systems are far more common with partial melting. It's when your melt and your solid don't remain in contact anymore. We have lots of evidences of this. Okay, so on a small scale, we see zoned crystals. All right. These zoned crystals, for example, like the plagioclase that we've talked about, you can see the different ways that it is bending the light, and you can see these kind of fun layers, these zones. Okay, and these zones are actually responding to the different chemical parameters. And as you can see over here with the Fish Canyon, so this is the Cottonwood Wash Tuff, but this is the Fish Canyon. You can actually see that there's like this calcic spike. And then you have more of this more sodic stuff that is growing on top of it. And so you're seeing this disequilibrium because we're sealing off what we just crystallized. We're sealing it off from the rest of the melt so that it can no longer communicate. So you don't even have to remove the melt to disconnect it from some of the crystals. So that's one of the evidences of small scale disequilibrium. Larger scale disequilibrium has to do with buoyancy. All right. So buoyant melting, that stuff is just going to head on out. So everything that's melted is going to move, but everything that's not stays behind. So the solid and the melt are actually becoming chemically isolated, not because they're just putting more crystal layers on, but because they are physically separated. So this is kind of a very basic way of looking at it. But here's your uniform parent rock. You start to melt, and of course, the first things you're going to melt are the felsic things because they have the lower melting temperature and stuff like that. Then you're going to actually separate out the felsic melt from the mafic remainder. Okay, this is probably one of the most common ways that partial melting occurs. Widespread, very significant. Okay, so your melt is going to be your magma. Okay, it's melted, so that makes sense. And it's going to be more silicic compared to the parent rock because those felsic minerals are the first ones that are going to go into the liquid. The stuff that gets left behind, we call restite. It's the rest of it. It's the remaining rock. And that is going to be depleted in silicic components, and it's going to be more mafic than the parent. And so, depending on how much you melt and how much you leave behind, you're going to have completely different compositions of what happens. Like, so differing degrees of melt produce different partial melt compositions. Differing compositions are going to produce different partial melt compositions. So we have a lot of variety that is possible here. And here's some kind of cool pictures. This is of Italy, Tajikistan, and and Wuhan, China. And this is really interesting. I kind of love that they have this big old rock that they, have taken a picture of and they've said, hey, look, this is restite. That's the stuff that gets left behind. Here's a leucosome, and a leucosome is actually when you have the melt and it gets trapped next to the restite. Okay, so it's these little dikes and stuff like that of really felsic stuff. How many of you guys have seen things that look like this? I mean, I've seen them at the bottom of the Grand Canyon. I've seen them in other places as well. This is a very common occurrence, partial melting. Okay. Well, now let's go to fractional crystallization. And keep in mind that fractional crystallization is when you have a melt and you start to cool it. So this is the most important way to diversify a magma from a rock is partial melting. And the most important way to diversify a magma from a liquid is to fractionally crystallize it. Okay, so it's the most important diversification process post melt. Okay, so remember this picture of the cottonwood wash tuff, and it's showing you that you've got a lot of crystallization going on. So as the melt begins to crystallize, sometimes you can segregate your remaining magma. So it's the opposite of partial melting, but it's not like reversing partial melting, if that makes sense. Because you've already removed your melt from the original rock, so you're not getting back to that original composition. You've taken out all that mafic stuff. Now you have the silicic stuff, and you're going to start modifying it. And so your melt starts crystallizing, the remaining magma becomes crystallizing. And so what are you going to see? Well, the stuff that crystallizes is going to be more mafic, and the stuff that is not crystallized is going to be more silicic. And you can actually see this in certain eruptions where it erupts the top first, and that is the more silicic stuff. And then as you go up in your deposit, so the very first stuff that's deposited is at the bottom, and then it continues to erupt, and you get more and more mafic as you go up through the eruption, which is pretty cool. But we do see that, and that means it was a zoned magma chamber because of fractional crystallization. Now, I talked briefly that I said, there's this assimilation and there's immiscibility and there's these other ones, but they're not as important. But assimilation is hot magmas melting surrounding rock, okay? And it's always mafic assimilating felsic because of the temperatures involved. If you have a felsic melt, it's not going to melt the mafic rocks around it. These cold mafic rocks are never going to get hot enough with your hot rhyolitic silicic lava. I mean magma. Okay, it's just not going to happen. So it's mafic assimilating felsic, and typically occurs in the continental crust because you have because of the temperatures, right? And it's difficult to do even in the continental crust because of how much heat you have to use to assimilate. So the question is, how do we even know this happens? Okay, so sometimes we're going to get big old xenoliths of this stuff. However, more often we see it in our chemistry. All right, so we can see xenoliths and xenocrysts, and that will show us that there was some assimilation going on, pieces of the country rock. But more importantly, we look at rubidium strontium isotopes. So essentially what's going on here, excuse me, is that rubidium is more abundant in the crust than it is in the mantle. All right, and rubidium actually decays to strontium 87. Okay. And so if you have a lot of rubidium in the crust, you're also going to have a lot of strontium 87 in the crust because that is what it decays to. So then if we want to look at our strontium 87, 86 ratios, so if 86 is stable, but not super abundant in the crust, but 87 is a decay product, so it's stable once it's done, but it comes from rubidium, which is ample in the crust. What's going to happen to your strontium 87, 86 ratio in the crust through geologic time? So basically what's going to happen is that if you have a rock that you think is from the mantle, and you're looking at that because of the trace elements, and you're looking at that because of the way the composition and stuff like that. So you've got this mantle derived rock, and it should have low strontium 87-86 ratios. Okay, so you should see not very much strontium 87 because strontium 87 resides in the crust. And if you're getting it from the mantle, you shouldn't see a lot of that, right? However, if you have a mantle derived rock based on other things, and all of a sudden you have evidence of crustal contamination, that if you have a higher 87-86 ratio, then that's your evidence for crustal contamination. Sorry, I said that backwards. If you have a mantle derived rock that has a high 87-86 ratio, then you have crustal contamination. And the nice thing about this is that all those other things we talked about, fractional crystallization, partial melting, stuff like that, that doesn't change your ratio of your radiogenic isotopes. So that's something that you can see regardless of how much melting or how much crystallization happened. Magma mixing, two magmas mixing underground. This does not happen. Okay, it's not as easy as having like lemonade concentrate and then putting water in and mixing the two together so you can have some lemonade to drink. All right, magmas don't want to mix together. All right, if you have a mafic magma, it's hot, it's more dense, and it's less viscous. If you have a felsic magma, and that's cold, not really cold, but less hot, more dense, I mean less dense and more viscous. They don't want to mix. They don't want to be in the same places, okay? There is evidence that this happens. It is super not common, and it seems to only happen right before eruption, as far as we can tell, okay? So basically, if we see things like disequilibrium mineral assemblages, so basically, if you have a magnesium-rich olivine and you have a quartz, you're like, those two don't belong together. Something had to happen to make them be in the same thing. Maybe it was magma mixing at the very end. If you have reverse zoning in crystals, that may indicate uh, magma mixing. The problem with that is there's lots of reasons you can have reverse zoning in crystals that don't have to do with magma mixing. You could be adding some new volatiles. You could be heating something up, all this type of stuff. So it gets a little dicey to try to figure it out. And magma mixing has a timing issue. The reason why we don't think it happens, except for right at the very end, is it won't take very long for things to equilibrate with each other. Okay, you've got something really hot, something really cold. They're going to come to a uh, a medium temperature. They're going to come to a medium density and stuff. One of the other problems is with the density contrast and the viscosity contrast, how are you going to mix things together? One's just going to be more viscous than the other. How are you going to force them to mix? Maybe convection, where you're having the movement because of the heat. That is a possibility, but it doesn't seem to be very common. Finally, we have liquid immiscibility, and this is pretty minor. Basically, what happens is as the magma is cooling, if it is an unusual magma, what happens is some of the compounds are not going to mix anymore. So once you get to a certain temperature, those are incompatible with each other. Not compatible, incompatible, like we were talking about with the trace elements. Sorry about that. Basically, what it is, if you think about you're boiling chicken soup, and everything looks fine and dandy, and then you take it off the stove and you come back 20 minutes later and there's these little pools of oil floating on the surface. Where did they come from? Well, they were perfectly happy to be together when they were hot, but as soon as they start getting cooler, they're going to separate, and that's called immiscibility. Where we see this happening more often is unusual magmas. Okay, sulfide rich melts might unmix from mafic melt. And this is really important because as soon as you get those little sulfides, they start to scavenge important minerals for us and important elements like chromium is an important element, and those sulfur rich melts will scavenge those up. And so then you'll have a layer of stuff that has a lot of chromium in it. And same with like the platinum group elements and things like that. So these are really important for economic geology, which is not this class. Sorry. And then the other place we see them are these really bizarre alkali-rich magmas that sometimes there's so much that it actually, as it's cooling, it unmixes from a less alkali-rich one. And maybe that's why we get volcanoes like Oldolongai, or maybe that's where we get kimberlites. Okay, those are some of the things that people are thinking about. but that may be possibly, but it's a very minor amount. It's very small volume. And so it's not something that we're going to spend a lot of time worrying about for this class. So keep in mind as we wrap this part up, magma diversification, almost every melt has undergone some type of diversification, okay? Whether that is partial melting, whether that's fractional crystallization, or these other things that we're talking about, they have undergone some kind of diversification. So they have a magma evolution, all right? They have a different composition than what was created during their first melt. And we come back to the idea that we have primary or primitive magmas and we have evolved magmas. And it's basically saying how much diversification has happened. Here's some possible test questions that I could come up from this material. I might ask you to name and explain 5 processes that cause magma diversification. I may ask you to explain crystal fractionation and partial melting and compare and contrast the two. I might ask you to tell me, how are you going to tell which kind it was? Was it fractional crystallization? Was it magma mixing? Was it partial melting? Like, what was it that caused any given magma series? Like, what kind of tests could you run from that? All right. Okay. Use the rest of your time this week to get caught up on everything, work on your labs, work on your homework, stuff like that. And then we will pick up again, starting to talk about basalts on Monday of next week or whatever week I come back, whatever that looks like for you. All right, you guys. And I hope you are having a fabulous week. And I will see you guys all later.